In this basic problem that I'm going to describe, it's just solving a 1D Laplace equation. So it's let's see, let's put this minus here. It's equal to 0. I'm just doing this in 1D for simplicity. And I'm going to impose the basic boundary conditions. Let's see. I always get that wrong. So u of 0 is going to be A, u of 1 is B. I'm just going to make A and B 0 and 1 because that gives us the very obvious solution, which will make testing the codes very easy. X is equal to X. And that's quite obviously the solution, since derivatives is 0 and satisfies the boundary conditions. Okay. I'm going to solve this using a basic finite difference stencil. Although my research interests are on finite element methods, I don't yet have the tools I need in Julia to do it that way, so finite difference stencil provides a very easy way to test this. Equal to 0. Let's put a minus in front. Okay. So this, since this is linear in the unknowns, ui, this can be abstractly written as a system of linear equations, which for the codes, I'm not actually going to construct the matrix A. I'll show you how I do that in a moment. And because of boundary conditions, the source vector v, 0 is going to be 0, and f of n is going to be, or n minus 2 actually, because of the two boundary points, it's going to be equal to 1. And that's just because the h squared goes away because we can multiply both sides by h squared. So this is a pretty typical problem, and I think it satisfies a lot of the workflow that you see in scientific computing. Let me show you what the C code looks like. Plus 1d.c. Okay, so I have the two functions. This guy calculates the right-hand side function a here, a times u. So again, I'm not constructing a. I'm not even using a sparse matrix representation. Let's go back to here. And then I'm going to have the driver, which actually calculates the solution. And the way I'm solving this problem is through a very primitive but simple iterative technique called Richardson's iteration, which looks basically something like this. So it's u arrow u plus alpha times u minus, or f minus a u. Although it's very simple, it represents a very, very typical solution process that you see in scientific computing. You start with the problem formulation, you get the discretization, and you use an iterative technique which doesn't require actual construction of the matrix A, but does require evaluations of A times U. And the iteration process is very typical. We have a residual evaluation process here. This is the Richardson iteration, but in more general iterative methods, this is an error approximation, and then an update, which in this case is just this. Now if alpha, this converges provided alpha is 2, whoops, put a 2 here, over the spectral radius of A. It's pretty easy to see that it converges for that. It's actually the same convergence theory as using forward Euler time stepping this actually is just basically a forward Euler iteration. So you can think of this as solving this problem by pretending it's the heat equation and then solving to a steady state. So I chose this because it's a very typical scientific computing workflow. And it's simple enough that I could implement it in a couple hours. I actually wrote most of this code while I was flying from Houston to Atlanta, and that's about an hour-and-a-half flight. So let's take a look at how I'm doing the stencil in C. So very basic. So I input the U that I want to apply A to. I have an output vector, and I have the number of grid points I want to use for the finite difference method. Okay, so here I do the boundary conditions. I notice I'm stopping at n-3 because the two boundary points are being fixed, so they're not actually part of the solution. And then I have the for loop, which goes through the stencil, and it's exactly what you expect it to be. And then down here in the driver, I set up the load vector, so it's all zeros here, except for at the endpoints, where I put in the boundary conditions. I set up the iterative method, and then here I don't actually test the tolerance for Richardson's method. I'm just giving it a number of iterations. I basically just tested it and picked a number of iterations that gave the right answer. This is just to make sure that all the codes are being treated equally. So yeah, here I evaluate the right-hand side, and then I perform the update. It's exactly the same update as you see right here. So it's U plus alpha. Okay, and then yeah. And here I just output the solution after so many iterations, and then of course memory management in C. This is pretty basic. So let's go to the first Julia code. This is something that a MATLAB program would come up with using using MATLAB syntax that you're familiar with. It produces perfectly functional code. So in MATLAB, in C I had a for loop, but in MATLAB you want to vectorize. We'll find out this isn't optimal for Julia, and I'll show that in a moment. Exclamation point means I modify one of the arguments. In this case, I'm modifying the out vector. I didn't know what kind of overheads doing a return would do, so I just kept it as close to the C as I could. So yeah, this is the vectorized stencil update and vectorized update formulas, and then outputs. And I have this debugging thing to actually construct the matrix. This was just to make sure that my stencil is correct, and it was. Okay, so I actually have these open in a Python notebook. So let's take a look. Oh, it might be important to show how I'm compiling the C code. So make file. Okay, it's a lot of flags. Some of these won't work on all systems because they use some of Clang's new optimization flags, like this guy here. I'm outputting a shared library so that I can call the function from Julia. That way I can use the same timing function. And then there's position independent code, O3 optimization, then various vectorization flags. Okay. So I'm going to put these all up in GitHub, and there's a top-level make. It'll just run through all the build process for you. So Julia interfaces with PyPlot, and here I'm including the initial Julia code, and it takes it a minute to load at first. Okay, setting up boundary conditions. What I said earlier was 0 and 1. Number of grid points 1,000. That's just so it doesn't solve instantly, and the timing can be relied on. Iteration parameter, this is actually optimal for this problem. It's independent of n because the spectral radius of A is never bigger than 4. Here's the number of iterations. I just guessed and checked until I got something that gave the right answer. Storage for outputs, and the discretized domain for plotting. So let's set that up. Okay, so here's the original C code. Julia has a facility that I like a lot. It has a very simple way to call shared library code. So here you put in a tuple. This is the driver function I showed you in C, and you put a colon in front of it. And then you also tell it where the shared library is. So here's the relative path to that shared library. Here's the return type. I just did void. The function signature, and this is how you do pointers here. And then another part of Julia I like a lot is the next step is you actually put in the arguments, but Julia will actually marshal the functions over to what C needs automatically. So if C expects a pointer to a float, and you put in a Julia array, which that is, see, then it will automatically just give over a pointer to the first entry so that I can use the C code immediately and not have to do any marshalling steps myself. And here I'm just timing it, and I plot it just to prove that it's giving the right answer. So this takes a few seconds. Okay, now I'm going to run the Julia code. You see I've already run it before, but let's go ahead and run that. Oh, that's just profiling stuff. Here we go. So the kernel's busy, it's running. Okay, I'll just take it a few seconds. So one of the things we're going to see actually, and I'll show it when I profile this. I already have done the profile just so we didn't have to run it twice. Is that the vectorized code, the lines containing the traditional MATLAB vectorized code, actually is taking quite a lot of time, and it's still running. Okay. Future runs don't take this long. I was actually a little bit surprised at how long it took with the vectorized code, but I think the whole point of including vectorized instructions in Julia is for convenience and concise representation when performance isn't necessary. We'll see in a moment what happens when I actually devectorize those. So yeah, so the plots, they're both correct. They gave us the right linear function. Okay, here's the ratio. So Julia with vectorized code is about 80 times slower than C, and I didn't want to have to run this again in the recording, so I went ahead and profiled it. So remember, don't optimize without profiling. And Julia uses a poor man's profiler. It samples the stack and gives you counts of functions that it sees in the backtrace. This is something I do in C a lot, except I use it through a debugger, and I'll just run random backtraces to see where hotspots are. It's effective and doesn't kill performance. So we see here that, so here's some top level stuff. And if we go down further in the tree, okay, so these are all just array codes from Julia. We can ignore these. What matters is where those things are being called in our code. And here we see line 16 and line 12 are giving a lot of trouble. So let's take a look at those lines. And you probably would have already anticipated, yep, so here's line 16. And that's exactly, that's a big hotspot. And should be another one, but we can ignore that for the moment. So one of the optimizations that's often used in some of the Julia forums I've seen is devectorization. So let me go to a devectorized code in here. Let me actually, so I have Laplace 1D underscore devec, where I've actually expanded out those for loops implicit in the vectorized code. So let's run a diff on that really quick. I'll show you exactly what changed. Laplace 1D devec out. So yeah, you see, this is the original code with the vectorized instructions, and here is the devectorized code. It looks a lot like C now, except of course the more MATLAB-esque loop here. Oh, and I've also put in type annotations. It turned out type annotations weren't that important for this problem, but I suspect in more sophisticated code it actually can make a difference, particularly if you're doing a lot of function overloading. Okay, And I've also devectorized the update step, which, as you see here, this was vectorized. Okay. Now let's see. That's supposed to be one of the major benefits of Julia, is the ability to write for loops without worrying about basically interpreter bloat causing a lot of performance hits. So let's shut down that. And let's open up the Julia. So here I load in the devectorized Julia. And I'm not sure why the first execution on the notebook always takes a few seconds. I'm not sure what it's doing, but it's no big deal. So same problem setup, everything's the same C code. I'm going to run that again. So yeah, it runs, correct answer. Now I'm going to run the devectorized Julia code. It'll run much faster. Okay, there it goes. So let's take a look at the timings. So the devectorized Julia is a lot faster than the vectorized Julia, but with on C, with all the optimization flags, it's about 5 times slower. So it's still not quite up to C standard, but this is pretty good, considering that if you did the same for loop in MATLAB, you wouldn't get this kind of result. And again, I just profiled it again. Here I can actually just run the profile, because this code runs a lot faster than the other one. Okay, same deal. Now it's not calling all of that array code from Julia, which it has to do for the vectorized code. Let's take a look. So it's looks like so line 15 and 16, those are exactly the same lines that were causing trouble in the other code. Let's get rid of the output. Plus 1d dvec. Take a look at 16, yep. So it's not obvious what we can do here to make this better. And then line 42 is another hotspot. Yep. And again, it's not obvious to me what I can do within Julia to make this better. But there are some really good tools out there that you can use in combination with Julia's facility to call C code. And that's actually what I did here. And I think this is actually a really effective way to write high-performance code, is to start off with something that works reasonably well, that you can write quickly, and then go through profiling iterations. And then the last step will be putting in highly optimal code that's produced from outside tools. In this case, I'm using a tool called ISPC, which uses LLVM as a backend to produce efficient vectorized code using vector registers and instructions that are in modern processors. A lot of people know about these things, but it's kind of hard to use them, because, especially in C, because compilers have to know a lot about your arrays and data dependency in order to emit vector code. So it's something it can't just do automatically, easily, without some kind of extra input from the programmer. So ISPC comes in here because it has a modified C-like syntax, which I'll show you here. You see, so I don't have syntax highlighting for this yet. Sorry about that. Modified C-like syntax, I have a for each loop, and this is basically just telling ISPC I want this to run efficiently on vector instructions. And I have the compilation process in the make file that'll do that automatically. And basically what I did is I took those two hotspots. Here's the inner stencil loop with the correct bounds there, and the update step for Richardson's iteration. And I'll show you how I included that into this Julia. It only took me a few minutes to do this. Plus 1d dvec and plus 1d ispc.julia out. So let's take a look. So I took the devectorized code, and I basically looked at it and said, okay, this is causing performance. Let's replace it And I actually wrote this in before even writing the ISPC code. I just figured out what the inputs and outputs should be and replaced this with a call to a C function. And I did the same thing here for the update and just replaced it with that. So I can't remember if I built it yet. It's built. Just as a quick, I'm not sure if ISPC can automatically generate shared libraries, so I had to do an extra step here to do that. Okay, let's take a look. And I'm including this even though it's not technically part of Julia, because in terms of programmer productivity, it only took me literally about 5 minutes to spot those hotspots. Okay, so again, I load in. It only took me a few minutes to figure out those hotspots and replace it with optimized kernels coming from ISPC. So Julia didn't do this for me, but it did provide a very efficient way for me to produce functional code. So again, run the C code, and now run the C code with ISPC. And the ratio time, so it's basically almost as fast as C, just probably insignificant difference there. We can run the profiler again to see if there's anything more we can do, but at this stage I don't know, aside from going deep into internals, I'm not sure what more can be done, so we can print that. And yeah, I mean, it's where you expect the problems to be, but again, here at this stage I could go into multi-threading, distributing the problem to the different cores, but I think this makes a relatively decent case that Julia can be a highly productive scientific computing language. Anyways, thank you for watching, and I think that's it.